Hi, thanks for joining our talk. My name is Mohsen, and I'm here with you and presenting our recent research. This is a collaboration between Arizona State University, WPI, and University of Minnesota. The name of the talk is The Snake, a practical mutation testing at binary level. The main idea behind this research is coming from the existence and the popular usage of the third-party components in embedded devices and in firmwares and also softwares. So we see third-party software components are an essential part of every IoT device. There is no IoT device without third-party components. Reinventing the wheel has never been productive. Buying versus building often favors reuse, whether through open source or cut solutions. With the benefits of reuse, there is a risk of security vulnerabilities hiding in the code. So here we want to go through, like as one of the examples, the compiler undefined behaviors also that can be introduced during the compilation process that programmer wrote a code, but while developer doesn't know that during the binary during the compilation and creating the binary, this vulnerability might happen because of an undefined behavior on the optimization of the compiler. So security properties like exploitability can only be determined on the final binary. Hence, software testing is important. So mutation testing is actually a meta testing. In meta testing, we are testing the test suite. So there is so in the regression test, we are trying to run the test based on the bugs that has been previously found. But a good test suite is just not only finding the previous bugs, but it should be able to catch any kind of bug and also another variant of the program. So when you are running the test suite on a variant of a program, which is actually a mutated version of the program, it should kill that test suite and it shouldn't pass. Testing is one of the most commonly used approaches in improving and maintaining software quality, but one challenge is that it can be difficult to measure the quality of the software test. The main goal of the testing is to find the bugs, but in a common steady state where all test suite passes on the current version of the software, how can we assess the tests and how actually can we know that how good our tests are? So mutation testing introduced a small change in the program. That change acts like a proxy for the real bug. And we test if the test suite can understand and distinguish between the real binary and the original binary and the mutated one. So how does binary mutation testing work? As we mentioned, binary mutation is a process of purposefully introducing faults in a program without having the source code. While in the definition of that there is not any criteria on the soundness of the resulting binary, the purpose of the test suite evaluation, based on the purpose for the purpose of test suite evaluation, we require the injected fault passes some health checks, which we call it as a trivial test. So like in any mutation testing, we have like a binary or source code that we apply some mutations on top of that using mutation engine, which is randomly selected from the mutation classes that it supports. And then we generate binaries and we test those binaries against the spec or the test suite to make sure how many of them is being killed and how many of them can pass the test. And during this phase, we can also find the trivial ones, which we are going to discuss later. In our research, we introduced 5 new classes of mutation: arithmetic, logical, conditional, constants, and skip, which is more than the previous study. The previous study, which published in the BAR back in 2019, only introduced 2 mutation class, and as part of the future work, they introduced having more as a future work, having more mutation classes supported. That's coming from the source level mutation. So as an example, for the arithmetic, we are replacing the arithmetic assignment operator with one of the set. Like in move ECX to the count, and we have a repeat instruction that repeats the decrement keyword pointer, the points to the ECI, ESI, to the number of count, and we change that decrement with the increment, and that's actually a mutation. How do these mutation operators represent bugs? So we're going to talk about one example in GCC. In one of the patches introduced in GCC, there's a function duplicate declarations that, as part of this function, there's a patch introduced that checks the types of the arguments passed, and if the old type is null, and the old type should be null, and then the new types shouldn't be null. When we go on the assembly level, we can see that that JNE on line 85C9CE for type R types checks for this constraint. And the patch that is introduced here, if we mutate the JNE to an unconditional jump, basically it reverts the patch and we take the fall through. And if the test suite does not include a test case that can identify such a mutant, then the test suite is not sufficient at capturing this kind of fault. Fortunately, GCC's test suite includes a test that can catch this mutation. Another version is on the compiler undefined behavior. Compiler optimizations can amplify the effects of undefined behavior. For example, consider the following code snippet that checks for a pointer overflow in the second if statement. That checks for buffer plus len is less than buffer. So where buffer is pointing to pointer, is a pointer actually, and len is a positive integer. The program's intention is to catch the case where len is large enough that buffer plus len wraps around. So, and because of the integer wrap around, it can bypass the first check. And since if we compile the code using GCC optimization, the second if will be skipped. There is the existence of vulnerability here, and which is the integer wraparound. And it is one of the cases that undefined behavior can be dangerous, and a test suite should have tests that support these cases, corner cases. How do we construct binary mutants? So let's talk about binary rewriting again. So binary rewriting is a process of modifying a compiled program in such a way that it remains executable and functional without accessing the source code. There are two ways to do binary rewriting, dynamic and static. Dynamic tools like Pin, DynamoRio, Cumulator, and Valgrind, they use different techniques to do this. On the right-hand side, we can see the Pin, which is one of the dynamic rewriters. As you can see, there are between the code cache and operating system, and also code cache and virtual machine, there are a bunch of back and forth control flow changes and context switches that can create a bunch of overhead when we use these tools. But here we are focusing on static rewriting. Static rewriting classified in three classes. Detouring, which basically hooks the underlying instruction. So this approach introduces a high performance degradation given the like two control flow transfers at the patch points. So how this works? In the patch-based instrumentation, actually, we're replacing the instruction with an unconditional branch to a new section. And then we change the control flow back to the patch point. To reducing the control flow transfers at the patch point, there is replica-based instrumentation, which basically places jump instruction at control flow changing destinations to a replicated code section. So we copy a new code the whole code section, including instrumentations, to a new section. And all memory references in this section are modified to maintain less control flow transfers within the original and replicated section. The downside is that the size of the resulting binary is noticeably increased. So we are focusing on reassembling, disassembly, and full translation methods. In reassembling disassembly, we're recovering the relocation table, so we create a relocatable binary by reconstructing the CFG, finding the function boundaries, and also doing symbolization. Ouroboros, which is used in the previous work, scans the data sections linearly and interprets any machine size word whose integer representation falls into a memory region and considers that one as a memory reference. This can introduce a bunch of false positives under compiler optimization. Randler improved this by content classification and using heuristics like localized DSA. However, Disassem, which we tested, results in 5 times faster um, output and use heuristics like register value analysis. And then full translation uses an IR and revenge that we are talking in the following. So these are the two. So basically in this research, we are comparing reassembling disassembly versus full translation methods. These two projects, the source code is available under the GitHub for Revenge and Disassem. Disassem works perfectly on all of the binaries that we tested in spec. However, Ouroboros reported problems with 2 of the binaries, GovMK and GCC, based on the previous paper. And also the previous paper, their rewriter was limited to a specific version of the GCC compiler. And while we tested Revenge, we noticed that an oversize in the final result of the binary, which is a magnitude to 35 to 75 times. Snake workflow for the Disassem. So, so basically, as you can see, the binary comes into the Disassem and we do symbolization and function recovery, and then finally we translate it to an IR, which is actually called Gitter. Gitter will be passed to Gitter capstone to provide us the byte intervals in the basic block, and we pass that one to mutation engine to perform mutations. As you can see, we have 5 classes of mutations. AOR replaces a logic operator with another a different logic operator. LCR replaces a constant operand, and ICR works by replace. So LCR is for the logical, ICR is for the replacing the constants, and ROR is for replacing the predicate of a comparison with another predicate, and finally ISR is for nopping an instruction or basically skipping the instruction. And finally, the results of the mutated good verbs will go to the Disassem compilation, or basically pretty printer, that we reassemble the files and we compile the binaries, and the binary will be passed to the trivial test. The successful passed binaries that health check will be passed to the spec runner to find which of them are killed or which of them passed the test. For the revenge, we rely on LLVM. So revenge works based on lifting the binary to TCG, tiny code generator of cumulator, and then afterward it does paralifting to LLVM. And then on the LLVM layer, we use source seeder, which is source to source and source to intermediate level mutation engine, which is from one of the previous works and studies. We apply our mutations over there, and or actually one mutation, and then we create and compile and link the binary. So the reason that we use LLVM, manipulating LLVM IR, is simple, and it comes with vast set of open source tools. And second is that applying changes to the IR language of a compiler will not allow generating code that is not compilable, and filters out the unsuitable mutations. The mutant categories. So mutant is a file that differs from the original binary only in one mutated instruction. Based on the results of the mutant execution, we have 3 steps: the killed, leave or pass, and then trivial. The killed mutants are the ones that cannot produce the expected test output. The leave or pass mutants that actually produce the output that test is looking for, and they pass the test. And the trivial ones are the mutants that, because of some exceptions or memory management errors, they fail the initial health check. Measuring the test quality. In order to measure the quality of tests, and actually there is mutation score. Mutation score is denoted as total number of killed mutants over the total number of the generated mutants. So one involved factor in achieving a higher mutation score is relevant to the reachability of mutated instruction or instructions, causing an exception that propagates the error all the way to a noticeable change in the program output. the more sections of the code test suite cover, the higher odds are for the test suite to detect the mutants. So, evaluation part. For the evaluation, we rely on SPEC 2006. There are 12 benchmarks written in C language, and we have 3 different input sets. Test is to confirm that binary is functional and is usually test used for trivial test or trivial check. Train used for the feedback-driven optimization, and finally ref, which is the actual workload and has higher code coverage and checks more functionalities of the program on the test. So for the experiment, we generated as many mutants as possible, and we selected 1,000 randomly select mutants for each of those candidates. For LBM, we only could generate 641 mutant, which is compared to the previous work, we were able to generate more mutants due to more richer mutation operator set. So number of possible mutations. As you can see for the LBM, for example, let's take a look at the GitHub size and LLVM IR size. So GitHub is the result of the Disassem before we apply mutation. It's about 190 kilobytes. But for the revenge, for the same binary, it's about 14 megabytes, which is so large. And some of them, for example, for Perl bench, it increases up to 1 gigabyte. But as you can see, the number of the mutations, revenge generates more mutants actually. Finally, the mutation scores after we run the test, which is the number of the mutants that killed on the y-axis, and on the x-axis we have all of our benchmarks. So as you can see, for almost all of them, the trend is that ref test killed more mutants because it covers most parts. It covers like most of the cases and most parts of the code. Except for Perl-bench that we describe in the paper, that Perl-bench test suite used the real Perl example and samples, which that's why it killed more in the test. And then we categorize mutants based on the killed, past, and trivial ones. As you can see, BZIP2 killed most of the generated mutants. And for lead quantum, we have the most of the trivial basically mutants. That's out of the 1,000 mutant we generated. And as we mentioned, for the LBM we have 641 mutants generated using Disassem. All of these tests are for the ref input set. And another categorization based on the 5 different classes of mutation we have. As you can see, for example, for GCC, since most portion of the GCC code base consists of branches, here it complies with that one, and we have 44.2% of the whole killed mutants for the ref input set of GCC are branch. And compared to the previous work, we see that rather than the branch instructions, arithmetic operations and constants also plays an important role in mutation. But the limitations of revenge, we couldn't finally finish all of the tests for the revenge because of 2 main reasons. The first one is the generated binary size. As you can see, just for this program on the left-hand side, it's a simple program, and this is the original CFG for this program. When we try to recompile that from using revenge, here is a CFG generated, which actually the translator for revenge adds a bunch of cumulative related functions to the control flow. And as you can see, for even like for example for LVM, overhead size overhead of the Disassem resulting binary is almost 1, but for revenge is 50 times larger, and it goes up to about 70 times larger. And so this is the first reason. The second reason is the runtime overhead. So execution time is slowdown for Ouroboros and Disassem imposes about 1% slowdown in the reassembled binary. Revenge introduces up to 10% slowdown in the compiled binary. Instrumentation overhead for Disassem takes about 40 seconds on average to generate GitHub file for a spec binary, while we spend roughly 25 second reassembling time for each mutant. On the other side, Revenge takes 15 minutes on average to generate the LLVM file and roughly 4 minutes to compile the binary, compile that LLVM back to the mutated binary. So as part of the future work, so here we introduced new classes of mutation ported from the source level, but we didn't map those to the real vulnerabilities that can happen, real bugs that can happen. For example, like the specific patterns, right? Like read after write or write after read that might cause double fetch sort of vulnerabilities, or even out of line vulnerabilities, or even like um, integer wraparound. So we didn't match those to the real vulnerability that can be introduced based on the mutation. So that can be added for the future. The other thing, so we are actually inserting faults. So what are the countermeasures for recovering from these faults and also detecting these faults? So we have another paper recently published in DAC for fault injection countermeasures, but we only considered the instruction skip as the future work. This work can be extended to support more set of mutations like arithmetic operations and other classes of mutations. The other thing is that generating the targeted mutants. So here we didn't do any mutation equivalence. So there are some of the equivalent mutants generated, and it can be determined by running the original binary and the mutated one and taking the trace and then finding where actually these two execution diverge. And yeah, so that's the end of my talk. Thank you for listening to me. And I would like to say special thanks to my collaborators and bar committee for their constructive reviews. Here's the link to the repo, including the source code for the project and the test suite. And I would be happy to answer your questions if you have any questions. Thank you so much.